talking about linear relations. What is the root of the word linear? Yes, line. Okay? So we're going to be talking about line relations, basically. Now, that just means that when you relate the two to each other, they make a nice straight line. Okay? And there's hundreds of different types of relations. The most basic is called the linear relation. Okay? And then there's the quadratic. Right? Then there's the third degree relation, and fourth degree, and fifth degree, and sixth degree. Okay? And they obviously go on from there. But you're going to have to know the first to the third very well by time you graduate. And it's a good thing to start from 1. Okay? A linear relation is a relation with a constant rate of change. So a relation with a constant rate of change. It is in the form y equals mx plus b. Now, m is the rate of change. That's also called the slope of the graph, which we'll be talking more tomorrow. And b is the y-intercept. Okay, now for today, like I don't really want to put this, but because it's not always true, but it's the initial amount. And I could give you lots of arguments for that's not true, okay? But it's in the book like that, and I'm like, oh yeah, I could see that if we do really, really, really basic ones, but I can give you tons of examples where it's not the initial amount, right? But it is always the y-intercept. That means where it goes to the y-axis, okay? Now, what we're going to do is I'm going to show you some linear relations and some non-linear relations to even get you to think about the two ways. Now, at a local celebration, the organizers put on a fireworks display. Assume that there are 20 fireworks sent off each minute. Assign a variable to represent the number of fireworks and the time in minutes. Okay, so yeah. Well, we can actually assign a variable. Okay. So we could say F is number of firearms. That's what's in here. But I actually like N for always number. Okay. So N equals number of firearms. Fireworks. Sorry. Yeah, you know where my head is at. I just saw a couple of you today and I was thinking firearms. I don't know why. Yeah, it's on YouTube. Yeah, now I have a motive. Okay, so, and then a nice common one for time is usually T, time in minutes. No, because time is, T is such a standard variable across physics. You guys haven't got into that in science, have you? Next. Oh. No, it wouldn't be wrong. As long as you say them correctly. Now, yeah, there's one that you're just going to always T is time, okay? S stands for? No, as a variable? No. Not even going to tell you because you get all mad. Time, fireworks. Okay, so let's just do like a graph here. At 0 time, what would be the fireworks? 0. Okay. Now, after 1 minute, there would be 20. After 2 minutes, 40. After 3 minutes, 60. And after 4 minutes, 80. Okay? So, which one should we put on the bottom? Time, which is usually there because then people could say, but you're controlling how much fireworks you're putting off, but we're really keeping the fireworks or the time very standard. Yeah? Good question. Not very often. Okay? So that is quite a standard to put time on the bottom because the only way that it would be on the side maybe is say I was putting fertilizer in a plant and I listed the time that it got to that height and then the time that it got to the next height. So the amount of fertilizer I would be putting down and then what would come out of it is what time it grows to that height. Okay? Like if you see bamboo grows by the minute, right? Very, very fast growing plant, right? So of course, people would be looking at the best way to optimize that by amount of fertilizer and water, right? So that's one that time could be on the side, and the amount of fertilizer or water would be what you controlled as a researcher. And then here we'll put fireworks. Okay, and our time would be 0, 1, 2, 3, and 4. And our we got 20, 40, 60, and 80. Okay, so we've got at 0, 0. And then we've got 40 at 2 minutes. We've got 60 for 3 minutes and 80 for 4 minutes. Now, to see if it is linear or nonlinear, which one? It is linear. And it is linear, why? Because it's straight. Now, could the values of time be something other than whole numbers? So, here's a question for you. At 30 seconds, would 10 fireworks go off? No, I'm doing it every minute. I'm putting it at the minute, I'm launching them. So at 30 seconds, how much fireworks has gone off? 40? 50 seconds, still 0. So would we be drawing a line through those points? No. This is what we call discrete data. And the other thing too is we can't have decimal fireworks even. So that's called interpolation. If you can find data within your data. So at 30 seconds, would we have 10 fireworks go off? You would go, no, no, no. So you can't really, the only thing you can interpolate here is after 30 seconds, there'd be no fireworks. After 40 seconds, there'd be no fireworks. At 1 minute, there'd be 20. At 1.5 minutes, I guess there'd still be 20 that have gone off, right? But those 20 have done their thing, and then they're going to wait. And then they're going to go again, okay? So it's discrete data. We can't have decimal fireworks, so do not join the points. Even though it's a linear relation, we're not drawing a line. Okay? But they are in a line. Okay? They're lined up nice. If you see something like this, starts here, then goes there, then goes there, then goes there. Okay? That's a nonlinear, hence the curve. Yes?
So, with the graph for fireworks and time, you're just supposed to assume that all 20 of the fireworks go off exactly at the 1 minute mark?
Exactly.
And you can't, like, assume another rate for them?
Right. You can't put in information that... so you can either talk to Greg. I think he has some. Yep. No worries. Okay. Okay, so let's go on to the next one. Now, an empty juice carton weighs 2 kilograms. Each liter of orange juice added weighs 1 kilogram. Complete the table to show the mass of the carton with each number of liters of orange juice in it. Okay, so at 0 liters put in, how much does that weigh? 2 kilograms. Okay, if I put 1 liter of orange juice in it, how much would it weigh? 3. And you can see it would be 4, 5, 6, and 7. Okay, so we're going to put number of liters of juice on the side. And here we will put mass, which is kilograms. Okay. Now, at 0, let's do 0, 1, 2, 3, 4, 5, 6, and then 0, 1, 2, 3, 4, 5, 6. Yeah, but you kind of don't know. We could go by 2s, we could go by whatever, right? But efficiency isn't, we're just going to make a little graph here because like I don't even have enough. I got to go up to 7, right? So if I needed to go to 15, which isn't unreasonable, I would have ran out if I would have went every second one, or if I would have, right? Okay, at 0, so on the bottom, with 0 liters, how much does it weigh? 2, so we're going to put that in. At 1 liter put in, it would weigh 3. At 2, 4, 3, 5, 4, 6, 5, 7. Now, if we called this X and this Y, could someone give me a formula for this, okay? I want you to think about it. What is the formula that is working for this? Yes? Y equals 1x plus 2, or x plus 2, doesn't matter. Is this in the form mx plus b? Yeah. So, and you can see where on this one, the b is supposed to be the initial amount. Would that be the initial? Would that be true here? And then our slope is 1. And you guys, did you do slope like in the past? Okay. Slope is rise over run. And we'll do more of that tomorrow. But you rise 1, run 1. So you go up 1, over 1. So that's where you get rise over run is 1 over 1. So you get an m of 1. Okay, that's my m value. So like this right here, say I had a point here and then a point here. The slope would be rise is 2, run is 1. So the slope is 2 on that one. Okay, and the bigger the number, the bigger the slope, because this would be 3 over 1, right? So it'd be 3 over 1, slope is 3, okay? So we'll do more of that tomorrow. But then you can see why this is a slope of 1, because it's rise 1, run, okay? So up 1 over 1, up 1 over 1, okay? Should the points be joined? Is it possible to put 0.001 liters in there? Sure is. Can we have decimal liters? Can we have decimal mass? Makes sense, right? So I would join this one because this would give me, I could interpolate in between there from this, and that's where graphing, now I know at your age, when I was your age, I'm like, okay, graphing is not that amazing. Okay, it's not like that. But the cool thing about graphing is how now you just graph a few pieces of data, and now you have over 1 trillion pieces of information. Because I can find out all of the data in between here, find all of the data in between here. And that's where data can be useful. If it shows a nice trend, it can be used to save like a lot of money, a lot of hassle, a lot of time, right? Because you can like find out conclusions. And not only that, you can extrapolate. You can go, it's following this pattern. Let's just keep going with the pattern. I bet you this will happen then, right? So populations, things like that, you know, debt, national debt, it's going this trend in 17 years. We probably will not have enough money to, we've got to put something into place, okay? The whole climate change thing, right? It's following a very, very close trend. And they're getting all this information from it, and if it weren't for that, your generation would not be cleaning things up, okay? If people didn't, Kate, are you paying attention, or do you need to go out there, or what? Okay. Now, the following this stuff, right, can show, you know, people are, and it's taken a while, right? But you wouldn't believe how when your parents were kids, there was no data on smoking, okay? And definitely when your, you know, grandparents were growing up, people smoked. What was wrong with it, right? Yeah, well, they had a lot of people. I mean, the commercials, it was like awesome. And the tobacco industry put in millions of dollars to tell you how awesome it is for you and the whole thing. And there was no data, right? So now, there is like zero doubt. So in like one generation, it went from stuff's pretty good for you to there is no doubt that it's harmful. And there's no doubt that it's harmful to kids. And there's no doubt that secondhand smoke affects people. There's just no doubt. They can prove it. They've proved it through data. They've proved it through, you know, cancer rates going up and throat cancer, and you know, they make a correlation between like people getting throat cancer and people who don't smoke, very low, right? And all of this stuff in one generation. And do you think that was done just out of anecdotal audience, or evidence, just people talking and saying, yeah, I think it's not good for you, okay? No, they have all the medical research, and they've done all the studies, and, you know, so, you know, and that's why, you know, when new medications come out, right, you'll see people are always, you know, people that are very well read and stuff, they're very, you know, oh yeah, it's a new medication, it's you know, it's awesome. You know, 20 years ago, 30 years ago, there's new medications that were awesome, and some of them are off the shelves now because they're harmful, right? And unfortunately, it takes time, and it takes data, and it takes these kind of studies, and they graph it, and they do their research, and come up with this stuff, and they can show trends, okay? Now, let's keep going here. We got the population of mosquitoes in a particular swamp starts with 10, but every day the population doubles. Graph the function, okay? So right when we start, how many mosquitoes we got? 10, okay? So tomorrow, how much would we have? Okay, because we're doubling, right? Maybe you want to just kind of circle that, doubles. Next day, 40, next day, next day, next day. Okay, now, I think we could probably go time on the bottom. Okay, so we've got 0. We could split this one up. Let's go by 1, 2, 3, 4, 5. At the sign, we're going to do number of mosquitoes. We could go by, I think we're going to have to go by 10s here. No, we're going to have to go by, like, even 20s wouldn't do it. I don't have enough. Is there, I got to go by 40s. So 40, 80, 120, 160, 200, 240, 280, 320, 360. Okay? So we start with 0. We would have 10. Okay? So you're going to have to kind of eyeball it, right? You don't want it right on 0, but you want it kind of a quarter up. After 1 day, we'd have 20. Okay? Then after 2 days, we're finally at 40. After 3 days, we're at 80. At 4 days, we're at 160. 5 days, we're at 320. Okay, is this a linear relationship? No. Okay, obviously not a line. Now, anyone come up with a formula for this one? If this was x and this is y, what would be, yeah, try it. Okay, if I did y equals x plus 10, that would be a linear relationship, wouldn't it? Because it's mx plus b. But if I take 5, if this is x, 5 plus 10 isn't 320. So that one wouldn't work, right? This is my x. I should be able to put in my x and get out 320. Okay, so basically, what can you do to 5 to get the answer 320? What can you get? Yeah? Okay, let me say it's 10 times 2 times 10 to the power, but we don't know. It's got to be y equals. Okay, but you know what? Look at this. This is 1 times 10, isn't it? This is 2 times 10. This is 4 times 10. This is 8 times 10. Right? Do you see that? So what do you have to do to 0 to get 1, 1 to get 2, 2 to get 4, 3 to get 8? Okay, so I'm going to, so this would be the same thing as y equals 10 times 2 to the x. Okay, so just try it out. No, because you had 2 to the y. You said 2 to the y. Oh. So you meant opposite to what you said. Okay. Okay. So if I put in 3 here, what's 2 cubed? 8 times 10? 80. Right? So this is what we call an exponential. Right? This is going up exponentially. And okay, exponential is very, very dangerous. Okay? This is your cancer cells. Right? They reproduce exponentially. So if you can catch them early, right? They always say, got to catch it early. If you catch it early before they get out of control, it's so much easier to combat, right? But if you let it go, because they they double every day, they get to where they're at a point where it's like it's gone in other places. Now here's a good question: should the points be joined? And I want a yes or no, but I want a why. That's going to be the harder part. Yeah? Okay, why? Okay, so that would be the argument for we should join the points. Is there an argument for we shouldn't? Yeah? That's where I would say would be a good argument. You can't have a decimal mosquito. Okay? Now, but on one side of it, you'd be like, but it's not like it's like 24 hours, ding, and they go, right? and then 24 hours, ding, and they go again, right? But, so this is kind of a weird question, because if you were down to the mosquito, right, and even when they give populations of, like, they'll say Canada's population growth is 2.1, right? People are like, oh, you have 0.1 of a baby, like, you don't want to be that thing, right? So it's a statistic. So I would say there's two arguments for it. Okay? So if you said yes, because it's not like it just happens, like at every minute, like the 30 seconds, nothing's happening, right? There would be stuff happening at 30 seconds. So I agree with that one. And then I agree with you can't have a decimal mosquito, right? So it's kind of your argument would be more important. So you could say no, can't have a decimal mosquito. And you know what? And that's what it would probably say in the book. You would just give this one simple answer, right? But I would say, or yes, because the population changes in between example 1 and 2 minutes, right? So for me, I think it would be more important of why did you say that, okay? Because really, in the true scientific journals, you could have at 30 seconds, there would be 10 point, or maybe 16.2 mosquitoes, okay? And in the scientific world, they know that that's really close to 16, right? They know that you don't mean that there'd be 16.2, but it would still give you a really good idea at that point how many there are. Yes, Zach.
When we do domain range, just how we can say that X or Y are real, can we say X or Y are real?
Yep. Yeah. Yeah, you would have to. But this one, you would list them all. You would just list them, I think. But if it was going forever, you would just say X is in the whole numbers.
Yeah. And then you could draw the line between those lines for X.
Right, but then you'd be calling it reals. If you join the lines. Yes.
On this question with, that would be like in a perfect world, with yes, that would probably be.
Well, yes would be what they call theoretical. Okay? Like in theory, if you have two football teams go against each other and one is way, way better than the other, in theory, that team should win. Okay? That's in theory. If you have two horses and the one horse is bigger, stronger, taller, faster, should win. But other factors get involved, right? And we know all about that stuff. I mean, they make Disney movies all the time about that stuff, the underdog winning. Okay? The underdog's not supposed to win, hence the name the underdog. When you go to Vegas and you bet on the underdog, right? Great chance you're going to lose. But when you win big, right? So this would be the theoretical answer, and this would be the what we call real life or application answer. Okay? And I would not, and then people would just sit and debate for like hours about these things, and I'd be like, hey, who really cares? We got to figure it out. Okay? You're both right. Just depends the way you're looking at it. Okay? Now, determine whether each relation is linear or nonlinear. Okay? So, what would this one be? Linear or nonlinear? Why? One simple answer for this one. Yes? Okay, there's no power. So it's what degree is this? It's called degree 1. So A, it's degree 1. So it will be linear at degree 1. And it's in the form y equals mx plus b. Now you got to be kind of careful with these too, because it can be degree 0. So y equals, say, 5. Y equals 5 is this graph right here. That's the graph y equals 5. Okay? So, like, if it's the amount of, like, say you get an allowance every week, $5. The amount of work you do equals allowance, right? You get $5 if you do nothing. Well, that probably wouldn't go over well. But you do $5 if you do nothing. Maybe you do if you like built the whole house, right? You get $5, right? That would be the relation for how much work you do for what your allowance is, right? No matter if you put in 0 minutes or if you put in 100 minutes, it's still a linear relationship though, because it's a line, okay? And that's the most simplistic linear relationship is y equals a constant. Okay, so hopefully you've written that down because I might even be able to quiz you on something like that. Okay, how about B? Okay, well, what is this going up by? No, what's the x is going up by? 1. Okay, this is going up by 3, then it's going up by 5, then it's going up by 7, right? So it's not linear. Because it should be going up by the same amount every time if it is linear. Okay, 0, 0, negative 2, 0, 1, 0, 4, 0, 7, 0. Okay. Yep, so you got 0, 0. Oh, negative 2 zeros over there. 1, 0. Right, 4, 0, 7, 0. So y is always the second one. Here's y of 0. Okay, this is x. Okay, so it makes a line. So I would say it's linear. What kind of line is it? Horizontal, right? Okay, D. Linear or nonlinear? Okay, that one's pretty basic, right? Why? Because it's not making a line. Okay, it's not constant. Okay, and then when you do something that's linear like this, you can find the slope quite easy because it's the same everywhere. But look at D. Do you see how the slope is very different at very different places? There's a slope, then there's a slope. There's a slope. Okay, it gets kind of steeper, right? So if the slope changes, obviously it's not linear. It's not a constant function. Okay, so we're working on page 308. It's pretty quick stuff, but make sure you're doing it because I had students not do that well on the quiz. Well, I should say not do that well. I got one wrong in the quiz because, I don't know, that question was right off the quiz, the one they got wrong. So maybe we're going too quick.